right. I always, well, I have to download the videos after class, of course, and then I post them on YouTube. But I just check to make sure that the sound is fine. So every class I start with, okay, let's start this recording. Okay, let's start this recording. So today I'm not gonna say it, I'm just gonna talk about it. All right. So, this week it's just rules, 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 and more rules. And basically, we have to memorize this sheet at the end of the day. No formula sheets. So if that means, I always found that taping it up in the bathroom, I know that's weird, but usually that helps. It's like, okay, got it. Anyways, whatever you got to do to memorize these things. A lot of them will just kind of like play out. We saw the product rule, or we didn't see the product rule. We saw the sum and the difference rules. So just as a quick review, right? Because last day we started moving away from actually taking limits, and now we finally just get to differentiate, right? To find the slope of the tangent line. And so just as a quick review, right? We said that, well, the sum and the difference rules, which is basically what we got to. I don't have my, I cleaned out my binder, so I don't have them. I can't really remember if we did anything else. I think that's what we got to. Say that if we want to take the derivative, d dx, of something like f of x, and it can be plus or minus, so I'm gonna do both because they behave the same way, of g of x. Well, if we're taking the sum or the difference, right, then we can just pull that derivative on top, right, or the d dx, the differential operator. And so then we get d dx of f of x plus d dx g of x. So here, for sums and differences, we can, and I call it just pull the derivative inside, right? We can pull that differential operator inside. We can pull the differential operator inside. Okay. What we'll see today is that is not, I repeat, that is not the case for multiplying and dividing functions. Okay. And so they're going to be a little bit trickier, right? So as soon as you've got a sum or a difference, then you're off to the races. You just pull that derivative onto all the x's and find the derivative, right? We talked about the derivative of a polynomial. We essentially just bring the power down in front and decrease the power by 1. So, and those rules are on your handout. Let me see if I can steal it here. I can, because that's how I made it. Right, so we talked about, well, we talked about the derivative of a constant is 0. Right, I'll just underline all the ones that we did last day. we talked about, okay, well, if I have x to the power of any n, we kind of explored how it behaved for just n equals 2, 3, and 4, I want to say. Yeah. But then we said, okay, with a little bit more proof, we could show that it applies for any n, right? And so the derivative of x to the power of n is just n times x to the power of n minus 1. And we also talked about e to the x. E to the x is a special derivative, right? Because it just ends up being itself, right? If you think about what that means in terms of the slope of the tangent line, well, that means that the slope of the tangent line of e to the x is just the same as the value of y, right? So that's an interesting property. We also said that, okay, if we've got a constant times a function and we want to take the derivative, well, that constant can just be pulled outside and we put the derivative on the function. And then again, we've got the sum rule and the difference rule in prime notation, right? Remember, you can use the d dx of f of x or just f prime if you want. And so today, this is the product rule, and this is the quotient rule. If we just have a look, right, and we'll write it out in a little bit here, just hand out some of these. Notice that we can't just pull in that prime or that little apostrophe, right? Which means we can't pull in that differential operator because it just doesn't work. And of course, we can prove this using the limit definition of the derivative. I don't want to do that. It's more important that you know how to use it. But for all of these, the textbook goes through all the proofs and stuff, but I'm thinking we just need to know how to do it. Do it, do it, do it. So that's kind of the end of our review here. Section 3.2 is the product and quotient rules. Side note, you have your test 2 on the first day back or on the Tuesday after reading break, right? And so it'll be up to 3.4, which we'll finish this week. So you'll get to spend all of reading break working on it, memorizing these formulas or differentiation rules. And then what I want to do is we're not going to have lecture after that test. And so what we'll do is we'll just kind of, if you have any questions for the first, well, max 50 minutes, then just bring those. We can go through those, because if you have questions, probably the group has the same questions, right? So if there's little things, obviously if there's big things, you need to get in touch with me over reading break. We can kind of hash it out. But if there's just little things like, oh, how do I do this? Or how do I just quickly, we'll take some time, go through some questions. And then once you guys feel ready, or we've maxed out our 50 minutes, whichever comes first, then you'll write your test. Okay? So, and I'll give you a same type of outline that I did for test 1 on Thursday, right? Where I just tell you what to expect. Although I feel like I've been better about telling you as we go. have to do this, you have to do this, to do this. So unlike sums and differences, oops. The derivative of a product, right? And I'll extend it to the quotient, although we'll start by talking about the product rule and then we'll move into the quotient rule, of a product and quotients. Oy. Of functions will not be the product or quotient of the derivatives. Will not be the product or quotient of the derivatives. And just because I want it on the same page, I'll deal with this page break here. We'll outline the product rule, but you've got it on your sheet, so, but I'll use the differential operators and then use the prime notation. D dx is the differential operators, prime is the, well, the prime notation. I don't know how else to say it. The apostrophe, I guess. So we do have to assume that f and g are differentiable, but that kind of goes without saying. So if f and g are differentiable, then the derivative d dx of f of x g of x, so now I've got a product in here, right? The product of two functions is going to be f of x times the derivative of g of x, bless you, plus g of x times the derivative of f of x. So we get two components here. Right. So we start with f of x, take the derivative of g, and then we start with g and then take the derivative of f. Or in prime notation, f times g prime is f g prime plus g f prime. Put a box around this here. It's on your handout, but we're going to use it a lot. A lot, a lot, a lot.
What notation was that?
Leibniz notation, the ddx with the differential operators. Yeah, it's Leibniz notation or differential. I'll just call this, I'll say this is a differential operator. Or I think it's LIE, Leibniz notation. It's the feuding Leibniz versus Newton notation, but we use both because we're fence sitters like that. So we use them interchangeably. Of course, prime notation is quite a bit easier on the eyes, right? And so usually if we have to memorize something, then that's the easier way to do it. But just remember that they're saying the exact same thing, right? So it could give you either way. On test 2, you will have to just spew out the product rule in prime notation. Okay? Same thing with the quotient rule and also the chain rule later, but we'll do that later this week. Okay? So just be prepared to just empty your brain, because I'm sure you'll have it memorized, and then you just got to write it down, and it's somewhere, I don't know, page 3 or something like that. Just write them down, and then you can refer to them.
So both of them or just the prime notation?
Just the prime notation. If you use the differential operators, I wouldn't care. They're the same. Don't mix the two in one go, though. That would be weird. But otherwise, either one that you prefer is fine. Okay, so what does this look like? Why would we even care? If f of x is x times e to the x, find f prime of x. I do want to give you guys a little bit of time to try it and see how it goes, right? Just being careful, because now you're multiplying two functions, right? X and e to the x. Let me just make sure. Good. Me too. So now, when we do these, or when we're asked to find a derivative, right, we have to be really careful to identify, okay, where are my functions, right, and try to break it down into as, so that you have these small functions, and just see what's going on, right? If you're multiplying functions, then we have to use the product rule. If we're dividing two functions, then we have to use the quotient rule. And sometimes we have to do it in pieces. Right? Quotient rule followed by the product rule, for example. We haven't talked about the quotient rule yet, but you've got it there. There's no mystery. Right? So if we talk about f of x is x times e to the x, right, then we can talk about x as being essentially our f and e as being basically our g. Even though f is already in there, it doesn't really matter. So then f prime of x, we know is going to be, and if we use just prime notation, because it's a little bit easier to look at, right? fg prime plus gf prime. Well, f is just going to stay x. G prime, g is just e to the x, and so g prime is also e to the x because of that special property of e to the x, right? The derivative of e to the x is e to the x, and then the derivative again, e to the x, it doesn't end. And so you've got e to the x. plus, and now g is just held steady, so e to the x times the derivative of x, we said was just 1, right? And if you think about x as just a x to the power of 1, right? It's going to be 1, but I'll outline why over here. D dx of x is just going to be d dx of x to the power of 1. Well, by those power rules, right, we said, well, that's going to be 1 times x to the power of 1 minus 1, which is 1 times x to the power of 0. Anything to the power of 0 is just 1. 1 times 1 is 1. We proved it. Done. Now we can just go ahead and assume that. You can derive it again if you have to, but once you're taking the derivative of x after all these nasties that we're going to do today, it'll be pretty good. So now we've got x times e to the x plus e to the x, and so we can pull out a common e to the x if we want, and so e to the x times x plus 1. Huh. Say that again? No? It wasn't for my ears. That's no fun at all. No fun at all. How about we do another example? If we have, that's it. So the derivative, remember, is the function for the slope of the tangent line, right? And the tangent line is the rate of change, right? Or the slope of the tangent line is the rate of change. So we're just talking about how quickly things are increasing or decreasing potentially. And so now we have a function for the derivative. So now we can plug in any value of x and see what the rate of change is at that point. The instantaneous rate of change.
From just that tangent.
Mm-hmm. At any value of x. Right. That's this whole course. Why, you may ask? There's lots of reasons, but it's basically building into integration, which is Calc 2, where you're finding the area under the curve, which leads into volumes and that kind of thing. So kind of getting you in there, working towards something. But for now, we just need to be really solid with our differentiation rules. So differentiate the function f of t is root t times a plus bt. Now I will highlight that we're not talking about f of x anymore, right? So now t is our variable in there. So we're going to differentiate with respect to t. So I'll make a note of that here. Oh, I put it on the wrong t here. Differentiate with respect to t instead of x now. Nothing changes, it's just we have to keep track of, because it can get confusing, right? If the b was an x instead, right? If I'm differentiating with respect to t, then x would be a constant, right? And we'll get into that later, but right, so we need to keep track of what we're differentiating with respect to. Okay. Just because I've got that page break, so I want to just highlight my two different functions, or what I'm going to use as my two different functions here. I've got f, and I'm going to let this whole chunk be g. Just so we get used to seeing both, right? Just so I'm not always using prime notation, right? Then let's do d dt of f of t is going to be let's just go straight to root t d dt of g, which is a plus bt, plus, and then we hold g steady, so a plus bt times the derivative d dt of root t. Remember to find the derivative of the root, right? We rewrite root t as t to the power of 1/2, and then we can bring that 1/2 down in front, and then we've got t to the power of 1/2 minus 1, puts us at negative 1/2, right? So we can still do that as long as we rewrite our roots as if they're powers, then we can still use the power rule. So if we've got root t stays the same, so that's fine. The derivative with respect to t of a plus b times t, this is essentially a polynomial, right? And so what we have is just a goes to 0, right? There's no t on a, so it goes to 0. And then b times t, t to the power of 1, bring that 1 down in front, t to the power of 1 minus 1, we get b. Plus, and then we'll keep the a plus bt steady. And then we're going to take the derivative of root t with respect to t. And so we get 1/2, put brackets around here just so we can keep track of them. 1/2 t to the 1/2 minus 1. Do this one in a couple of steps here. So we get root t, or how about we write b root t just so it looks nicer, plus a plus bt times 1/2 root t is what that would simplify to. If we want to combine these, try our best to simplify. We need a common denominator, right? And so we've got b root t, oops, not root 2, b root t times 2 root t over 2 root t usually I cheat and I don't necessarily use the least common denominator. I just multiply both sides by what I want in the denominator. Plus a plus bt over 2 root t. Now they're both over 2 root t, and so I've got b root t times 2 root t. So I'm going to pull that 2 out front because now I've got root t times root t plus a plus bt. I can ditch those brackets because there's no negatives, so I don't have to worry, over 2 root t. This becomes 2bt plus a plus bt over 2 root t. And then as a last step, let's just combine that 2bt plus 1bt to get 3bt plus a over 2 root t. And then I don't see anywhere else to go, so I'm tapping out. I do find that sometimes it can be hard to know when you're done simplifying, right? And there's often cases where you could keep going, but you just have to ask yourself, well, would there be a benefit to the simplification that I'm about to do, or is it just going to be another, is it going to look the same but just different? Right? And so, because I'm sure there's things that we could do, but I'm going to leave it there. Yeah.
Question. Review. So, how did you find D here again?
Do you mean?
Like D over T?
Oh, the d dt is a differential operator. So it's essentially the prime. So it just says take the derivative. The dt in the denominator is just saying take the derivative with respect to t, right? So
So it's not a D divided by dt?
it is sort of, but it's just an operator that we put on there to say, so here, if we just focus on this section here, right, d dt of a plus bt, well, this is saying take the derivative of this, right? And so what we did was, this one just transferred down here, the root t, but the derivative of a plus b times t with respect to t is just going to be b. And so that's where this b came from. Right? And so you can think of these ddt's or ddx as just primes, if you prefer. But that's why I wanted to do a couple of examples. I want to mix it up so I don't only use primes or only use this one, because you have to be kind of limber. So a lot of the time, right, if we go back to the function, it would have been easier if we could have just used the sum rule or the difference rule or even just the power rule, right? If we can convert something to something nice like a polynomial, right? We saw the derivative of a polynomial. Even if it was this huge polynomial, well, you just bring the power down, decrease the power by 1, bring the power down, decrease the power by 1, right? And it's just taking the derivative of a polynomial is really fun and really simple. So sometimes, instead of just jumping in and finding, okay, that's the product of two functions, great, product rule. What you want to ask yourself is, can I rewrite this basically to get a polynomial, right? Or something at least that's easier to deal with. And so in our case, sometimes it will be easier to differentiate a function if we manipulate it first. So consider the function, the previous function. We had f of t is root t times a plus bt. We can rewrite this, right, as t to the 1/2 first times a plus b times t. And then I can bring in that t to the 1/2. I get a to the times t to the 1/2 plus b times t. I'll write it to the 1 times t to the 1/2. Just to emphasize that I'm just bringing it in, which is a t to the 1/2 plus b t to the 1/2, 1 plus 1/2 t to the 3/2. Now, this is just a polynomial. Kind of a weird one, right? But it is. So after simplifying, we are able to avoid the product rule and only use the power rule. Oh, wow. After simplifying, we are able to avoid using the product rule and now only need to use the power rule. Only need to use the power rule. So f prime of t is going to be a times 1/2 t to the negative 1/2 plus b times 3/2 t to the 3/2 minus 1 is 1/2. We can rewrite this so it's not so weird. We get 1/2 at to the negative 1/2, or we can even write that more if we want, plus 3/2 bt to the 1/2. Even though it doesn't really necessarily look like it right now, right? Let's see here. Previously on Calc 1. We can rearrange things and we can convince ourselves that these two are the same. Equivalent to the previous derivative. I'm gonna turn that. So you can see, but it's so sunny. I didn't even change that much. So we just have to get a little bit creative. As long as we follow just kind of math rules, right? Then if we can rewrite a function to be something that's easier to deal with, right? Then we don't have to go through with the product rule or even the quotient rule, right? Those two sometimes, if we're lucky, we can avoid them, right? Just by rewriting. If you're working on something like this on your own, right, what could you do to check to make sure that they're equivalent, right? Here it's, I would say it's pretty obvious that they're going to be the same, right? Oh, you can probably convince yourself that, oh, if I just put in some time and simplified this and move things around, right, I could probably get them to look the same. Sometimes it's hard to get two things to look the same, even though you're probably convinced that they are, right? And so one trick that you could use is just take one function and then subtract the other function in Maple, for example, right? That's probably your most powerful tool. But even, I don't know, I haven't really used Wolfram Alpha. It was kind of like after I was done school, I feel like. So, but Wolfram Alpha, basically the same thing. I'm sure that you can say, hey, take this function minus this function, right? This function minus this function, make sure that it equals 0. If it doesn't, then they're different, right? And so you can always use that trick just to make sure, if you're not sure if you arrived at the same answer. No, but as long as you follow legal math rules, because even if I see something that I'm like, oh, I don't know if that's the same, I just do that. I'm like, oh, is it the same as what I'm looking for? Yes or no? Cool, right. So, because we do need a little bit of creativity here, right? So sometimes we need to get creative and just kind of think, oh, how can I rearrange this? And we all approach that differently, right? So we'll end up with slightly different versions of the same answer, right? But we should get to the same answer. Cool. Are we ready for the quotient rule? It's more of the same. It's a little bit bigger, but that's okay. So the quotient rule of course, if f and g are differentiable, we have to say that, but if f and g are differentiable, then, and you have it on your sheet, but I'll do the Leibniz notation with the differential operators first, then d dx of f of x over g of x is going to be g of x times d dx of f of x minus f of x times d dx of g of x. Oops. All over g of x squared. G doesn't look like a G. Or, and I'm trying to keep it all on the same page here. In prime notation, which is the one that you have on your handout, the derivative of f over g is going to be g times f prime minus f times g prime over g squared. So we start with that g. And how I kind of had to remember it is the g in the quotient rule is the main player. So we start with g and then take the derivative of f minus hold f steady, the derivative of g, and then over g squared. And so there's no derivative in the denominator, right? It's just over g squared. similar, sort of, I would say, to the product rule, except now we're dividing by g squared and we're subtracting and we swap things. Okay, never mind. They're not similar at all. Swapped some things, subtracted some things instead of added, divided by g squared. So we do have to remember this one. And again, on the test, right, state the quotient rule in prime notation. Just tell me what it is. And that's really just so that you have it for the rest of the test. So get it out of your brain. Refer back to it. Okay. Let's do an example. If we let y, we've been using f of x, y and f of x are the same, right? So if y is x squared plus x minus 2 over x to the 3 plus 6, find y prime. So I'm going to break this down. So y is x squared plus x minus 2 over x to the 3 plus 6. I just want to highlight that in this case, this is our f, and this is our g. So if you wanted to, you could find the derivatives kind of independently and then smush them into the quotient rule. That's fine. But I'm just going to build them all in. So then y prime, and I am going to need quite a bit of room here. So I'll move it over. Y prime is g, just straight g. So we do x to the 3 plus 6 times, and I'll write out, look at what I've done in my notes. I've mixed the differential operators with the primes. I didn't even pay attention. How about this? d dx, or what we'll see later is we just call that dy dx. Differentiate y with respect to x. We want d dx of f, which is x squared plus x minus 2, minus, and now we hold f steady, x squared plus x minus 2, d dx of g, right, g prime, x to the 3 plus 6. And then all that, don't forget, is over g of x squared, which is x to the 3 plus 6 all squared. A lot of the time, because if we're using the quotient rule, we're always going to be over g of x squared. A lot of the time, it's not really worthwhile to expand this out and try to simplify. So we just kind of leave it. Unless you see an obvious kind of cancellation or whatever, I would just leave it as g squared.
This is the quotient rule?
Yeah. Like I said, there will be cases where, yeah, we will expand it and try to, get something out of it. But most often, nothing really happens down there, so we just keep it. Because now at least it's nice and compact, x to the 3 plus 6. If we had to do that squared, right, x to the 3 plus 6 times x to the 3 plus 6. It's a little bit bigger, a little bit nastier. So taking the derivatives now, right? X to the 3 plus 6 stays x to the 3 plus 6. Taking the derivative of x squared plus x minus 2, we get 2x plus 1. Because now we've just got a nice polynomial in there. Minus, and then x squared plus x minus 2 stays the same. And then we take the derivative of x to the 3 plus 6, which is just going to be 3x squared. Over x to the 3 plus 6 squared. We'll focus on the numerator, right? Because it looks like maybe some things might cancel out if we just expand and simplify. So let's do that. So I've got 2x to the 4th. Make sure I don't skip around here because doing last day. 2x to the 4th plus x to the 3 plus 12x plus 6 minus, and then I'll keep that negative outside the brackets for a little bit longer, just because I don't want to get ahead of myself and miss a negative. That would be bad. X squared times 3x squared is 3x to the 4th plus 3x to the 3 minus 6x squared all over x to the 3 plus 6 squared. And I guess if you're confident in your skills, then fine, you could have skipped that step, but usually I bungle it, so I usually take the extra step, because otherwise, oh man, you don't want to forget a negative. 2x to the 4 plus x to the 3 plus 12x plus 6 minus 3x to the 4 minus 3x to the 3 plus 6x squared all over x to the 3 plus 6 squared. It's coming together. We can collect some like terms here, right? We've got 2x to the 4th minus 3x to the 4 puts me at negative x to the 4. And I'll just show that I've used those up. And then I've got x to the 3 minus 3x to the 3, putting me at minus 2x to the 3. I've only got the 1x squared, so it's plus 6x squared. But I'll cross it off just to show that it's done. And then plus 12x plus 6. You guessed it, all over x to the 3 plus 6 squared.
Then do we extend the bottom one?
I wouldn't. I don't really see any cancellations that could be made. There's none popping out at me, so I would just leave it. So that's what I was saying. So most of the time, just leaving it as g squared, right? Because g was x to the 3 plus 6, and then so we've got g squared in the denominator. Usually we can just leave it. Unless we see, like if we could factor out an x to the 3 plus 6 out of that top, yeah, absolutely. Go ahead and do that. I don't see it, though. So I'm just gonna leave it. Any questions about that one? Okay. Let's do another example. Surprise. Put it on new page. Example. So I've been threatening about this, but it's true. Your lab exam, you're gonna have to find the equation of a tangent line to some curve, right? It's gonna involve the derivative. First, you have to take the derivative, because what's the derivative? The derivative is the slope of the tangent line. And then at some point, well, then you can use the point slope form, right? Because you've got a point and you can find the slope at that point using the derivative, and then you can make the equation for the tangent line. So that's what we're about to do here. So find the equation of the tangent line to the curve y equals e to the x. Oh, nice. As soon as we see e to the x, that is good news. Over 1 plus x squared. Oh, man. Had to be a quotient rule. That's okay. At the point x equals 1, it could just be at the point x equals 1, right? We could find the y value. Y is just e to the 1 over 1 plus 1 squared. Okay. And so that's where the 1/2 e comes from. Trying to keep it on the same line here, because we've got e over 2, however you want to write it, 1/2 e or e over 2. Okay, so we're going to find the equation of the tangent line to that curve at x equals 1. And I would highlight this at x equals 1. So we've got a point, which means if we've got the slope, then we can use the point slope form. So to use the point slope form, to find the equation of a line, or of the line, to find the equation of the tangent line, we need to find its slope. We need to find its slope at x equals 1. Right? That's the point that we're interested in. And the slope, the general function for the slope, is the derivative, right? And so here, what we're actually saying is we have to find the derivative at x equals 1. I want you to take a little bit of time, see what you can do, right? We've got a quotient, so you know you're gonna have to use the quotient rule. Try it out. First, find the derivative. Right, we'll focus on that. Go from there. So I'll get started here. Because I was about to write just dy dx. I'll just show you that they're the same. So d dx of y can be written as just dy dx. And you're just going to read it as differentiate y with respect to x. Of course, our f is e to the x and our g is 1 plus x squared. And so now if I want to have g is the first one out in front. And so g is, where is it? I'm looking at the wrong one. 1 plus x squared. And then I want d dx of e to the x, which we know is just e to the x, minus, and then f held steady is e to the x times d dx of 1 plus x squared, right? Essentially g prime over g squared 1 plus x squared squared. And again, I'm probably just going to leave that as just 1 plus x squared all squared. I'm not going to do anything with it. So taking the derivatives in the numerator, we get 1 plus x squared just stays the same. The derivative of e to the x is just e to the x minus e to the x times the derivative of 1 plus x squared puts me at 2x. Looks like I can pull out a common e to the x. So let's do that. Oh, haha. I almost forgot. Over 1 plus x squared squared. You don't want to leave it alone so much that you completely forget about it. That's bad. But if I pull out a common e to the x, then I have e to the x times 1 plus x squared minus 2x. Over 1 plus x squared all squared. I'd be fine if you left it like that, right? But let's try factoring it. E to the x times 1 minus x squared over 1 plus x squared squared. Bless you. So what you'll see, so there's nothing that we can cancel here, right? We're able to condense it just a smidge more. This is the function for the slope of the tangent line at any value of x. Okay. So dy dx is the function for the slope of the tangent line at any value of x. Usually, if I want to evaluate this function at 1, I would just say f of 1, for example, if I just have a function. But when we're talking about derivatives, what we do is we write, okay, well, I want dy dx, and then you just do a straight vertical line, and then down at the bottom you say x equals 1, and you're going to read this as dy dx evaluated at x equals 1. Because you'll see that so we want to get used to seeing it. So then in our case, dy dx evaluated at x equals 1, well, dy dx is e to the x, let me just steal it from up here, times 1 minus x squared over 1 plus x squared all squared. Same as when we take just f of 1, right? We're just going to plug in 1 wherever we see an x. And so we get equals e to the 1 times 1 minus 1 squared. Uh-oh, looks like a 0 to me. That's okay. Over 1 plus 1 squared all squared. So I get 0 over 2 squared over 4 is just still going to be 0, right? As long as I'm not dividing by 0, it's fine. What does this tell us? This tells us that at x equals 1, right, the slope of my tangent line is 0, which means I've got this horizontal tangent line. So knowing that the slope at x equals 1 is 0 actually tells me a lot about my curve, right? It means it's reached a peak there, right? Or a minimum. Usually it's a maximum or a minimum. So if the slope at x equals 1 is 0, we know we have a horizontal tangent line, whatever it looks like. We know we have a horizontal tangent line. We know the slope is 0. That doesn't mean it doesn't exist. It means it's just 0, and that's a thing, that's a physical property, right? And so we can still use the point slope form. We can still use the point slope form to find the equation of the tangent line. To find the equation of the tangent line. Another one of those things that you should probably just memorize. Y equals y naught, or sorry, y minus y naught is m times x minus x naught. Doesn't help if I say it wrong. Where x naught, y naught is the point that you know, and m is the slope. So the point that we know is that y minus, and then it was 1/2 e, right? Yeah, or e over 2 if you prefer. Y minus, sure, let's do e over 2, is the slope 0 times x minus 1. Well, it's just going to go to 0. So then we have y equals e over 2. Or 1/2 e if you prefer. With a slope of 0, y equals mx plus b is just y equals b, and that's okay, right? And so this is the equation of the tangent line. And if we're curious, the graph would look something like this, but this is where Desmos just comes in and saves the day. Something like this, I'm pretty sure. Not really to scale here. Y equals e over 2. Just like before, just want to emphasize that a lot of the time we can just rewrite a function, we can manipulate it a little bit and get a much easier function to deal with, right? Because what you've probably noticed is that the quotient rule, yeah, it's fun and all, but if we can avoid it, maybe that would be nice, right? So as soon as you see a quotient, of course, you're going to think quotient rule, but then your first step after that is going to be, okay, how can I avoid the quotient rule, right? You know you have to do it if there's no other way, but often there's going to be ways that you can manipulate something. And so as we found in the product rule case, it is usually a good idea. It's usually a good idea to see if we can manipulate a function to avoid the quotient rule. And sometimes we can. For example, if I have something like f of x is 3x squared plus 2 root x over x, I do have a quotient here. But maybe, just maybe, I can bring that x in the denominator up to the numerator, and then I've got a nice polynomial-esque thing. So here, we would have to use the quotient rule if we just went ahead and differentiated that as it is. But what we can do, 3x squared plus 2x to the 1/2 times x to the -1, right? That's why we need to be good with our exponents here, so that we can rewrite things. Bringing that x to the -1 inside, I've got 3x times 2 minus 1 plus 2x to the 1/2 minus 1, which is going to be 3x plus 2 to the x, or 2 times x to the -1/2. Now you just do the power rule and the sum rule, because just call it a polynomial. So a lot easier to deal with. Which equals much easier to differentiate. Woohoo. Any questions about the product rule or the quotient rule? How about everyone's favorite thing, trig functions? Ooh, I know. And, oh, I got it here. You've got the derivatives of the most common trig functions that we might have to use, right? You do have to memorize those, right? Because there's no formula sheet. You will need them, right? This is probably the bare minimum of what you'll need to memorize. But just remember, your brain's a muscle. Memorize all these things. I know. In real life, you can just look them up. Just do them. We like to make you work for it, I guess. It's not actually my preferred method, but anyways. Who am I to say? Where's my page break here? Maybe I'll put it on a new page. Section 3.3 is derivatives of trigonometric functions. Trigonometric functions. So I'm going to steal that little blurb from the handout here. Copy. Oh. When you memorize this table, there's a hint. You have to memorize this table. Memorize the derivatives. But it does have a helpful hint here, right? So if we look at, okay, let's look at the usual suspects, right? Sine x, cos x, tan x. So the derivative of sine is cos x. The derivative of cos x is negative sine x. The derivative of tan x is secant squared x. Ouch. Cosecant, negative cosecant x, cotangent x. Who knows what the logic is there? Well, how did we arrive at all these? We didn't arrive at anything, right? But we're able to use these because someone went through and used the limit definition of the derivative on each of these and figured out what they were, right? And so of course we can prove these. And again, they're in the textbook. And Steve was telling me that, I guess, I'm not surprised. There's a really nice video of the proof on Khan Academy. So if you're interested in the proof, then great, go look that up. But we're just going to use these, use them. Out of secant x, we get secant x again and tan x. Interesting. I guess same with cosecant. Less startling when it's negative or something. I don't know. So whatever you have to do, write a song or something to memorize these. If you do write a song, I would love to hear it. I would love to hear it. Okay, so we have these, right? You have them, and soon you'll have them memorized. I'll do my little disclaimer here. The proofs for most of these derivatives, are outlined in the textbook. Or if you're interested, and that's not a hint, it's just if you're interested, because it is kind of neat. Check out Khan Academy. Everyone's heard of Khan Academy, right? Yeah, if you haven't, probably underline it. Sal Khan is just so amazing. I don't know, he could take like the most complex thing and just feed it to you in like 7 minutes. It's amazing. Anyways, Khan Academy. It does mean that you have to know what you're looking for, and sometimes that's the hardest part, right? But after that. So for example, derivatives of trigonometric functions, I'm sure he has a video called that. All right. We will need to memorize the derivatives of trigonometric functions. But after that, right, sure, there can be quotient rules and product rules and sum rules, power rules, whatever. But as long as we know the derivatives of these things, then we can just use them. So we can jump straight into an example, actually, especially because you have them in front of you. So if we have to differentiate f of x equals secant x, clean that up, secant x over 1 plus tan x So we're going to differentiate that, and then we're going to think about, oops, I almost wrote it out again. For what values of x does f have a horizontal tangent line? That's what we just found in the previous example, right? We arrived at the slope being 0, right? So the derivative at x equals 1 was 0. And so then we said we have a horizontal tangent line. Now we're going to force a horizontal tangent line and see what values of x satisfy that. And that's usually what we do for optimization problems, right? And so if you've got a curve representing some sort of, let's say a profit function, right? Then if you can figure out where the top of that profit function is, that's your highest profit. And then you need to figure out, okay, what value of x yields that highest profit, for example, right? And so we do that where we set the slope of the tangent line equal to 0. and solve for x, usually in optimization, which is a pretty fun field. So for what values of x does the graph of f have a horizontal tangent? Horizontal tangent. If we take f of x as secant x over 1 plus tan x, we know we've got a quotient rule here, and our f is secant x, and our g is 1 plus tan x. So here I'll just highlight that we've got a quotient rule combined with our trig functions. They'll behave the same way though. Right. First, we're going to put g up top, differentiate f, minus f times the prime of g, or the differentiated g. Oh yeah, combining all my notations. It's okay. All right, so then f prime of x, I did it again, which makes me think that maybe that's what the textbook is doing. I'll stick to differential operators. Thanks. D dx of f of x is going to be g, so 1 plus tan x times d dx of secant x, g times f prime, minus f, which is secant x, times d dx, the derivative of g, of 1 plus tan x, all over g squared, which is 1 plus tan x squared. Again, we'll focus on the numerator. If something happens to cancel from the denominator, that's great, right? But it's not going to be our top priority because usually it's not going to happen. And so focusing on the numerator, we've got 1 plus tan x, we'll just leave that on its own and focus on the derivative of secant x. Since we don't have them memorized necessarily yet, the derivative of secant x is secant x tan x, then minus secant x, and then the derivative of 1 goes to 0, and the derivative of tan x, right? Because in there I've just got a sum, so I'm allowed to bring that derivative onto 1 and tan x, but the only thing left is the derivative of tan x, which is secant squared x. So now I've got times secant squared x. What I'm going to do is I'm just going to expand out, well, it's all over. It's all over. 1 plus tan x squared. I'm going to expand the 1 plus tan x times secant x tan x. So what I get is I get secant x tan x plus secant x tan squared x minus, and because I see a common secant x, I'm going to leave it as secant x times secant squared x. It doesn't really matter if you combine them and then pull them apart again, but secant x times secant squared x over 1 plus tan x squared. I'll pull out a common secant x. Secant x times tan x plus tan squared x minus secant squared x over 1 plus tan x squared. One identity that we're going to use here. No, say it isn't so. I know. But secant squared x is one of those ones that we'll probably see a bit, so you'll start to recognize it and memorize it. You can rewrite that as tan squared x plus 1. Or you can replace secant squared x with tan squared x plus 1. So now we've got secant x all on the outside times tan x plus tan squared x minus tan squared x plus 1 inside the brackets, right? So, or if you brought in the negative already, then that's good. Over 1 plus tan x squared as, yeah. You can replace with tan squared x plus 1. That's probably another identity to have on the roster. But now what we see is, okay, well, this tan squared x minus tan squared x, once I bring that negative in there, those are going to go away. So now I'm left with secant x times tan x minus 1 over 1 plus tan x squared. Yeah. Never mind, never mind. So now, right, this is the slope of the tangent line at any value of x. But we want to force this tangent line to be horizontal, right? So have a slope of 0. And so since we want to find the values of x that yield horizontal tangent lines, we need to find the values of x that make the derivative 0, right? Because that's the same. Horizontal tangent line is a derivative equal to 0. So we need to find the values of x that make the derivative equal to 0. If we look at secant x, right, so if we write this out here, what notation did we use? So d dx of f of x, we said was, and I'll just steal it from here, is secant x times tan x minus 1 over 1 plus tan x squared And you can definitely use Desmos to check each of these individually, right, to check your arguments, but secant x will never be 0. So that's just secant x. Will never be 0. There's nothing that the denominator could do to yield a 0, right? So it can never get you to 0, because even if you set it to 0, then you're dividing by 0, and that can't be done. That's illegal math. And so this will never yield d dx f of x equal to 0. So our only hope is that tan x minus 1 has to be 0, right, to get us to 0. Need this to equal 0. So what we say is, okay, well, at tan x minus 1, if I'm going to force it to equal 0, then really what I'm looking for is where tan x equals 1. And this happens at n pi plus pi over 4. At x equals n pi plus pi over 4. You can use Desmos or whatever. Tan has a period of pi, right? So where n is an integer, and tan x equals 1. The first point tan x equals 1 is pi over 4. And then because we've got that period of pi, right, at every n pi, that's going to repeat itself. Therefore, we have horizontal tangents, or horizontal tangent lines, at x equals n pi plus pi over 4. And I'll just add where n is an integer. Oops. And I think we'll save my next 2 examples for review next day. How about that? Any questions though? No? So we are doing the chain rule. Chain rule next day. And then that'll be it for test 2. Right? So that's what we're finishing this week. But the chain rule is a little bit big, so we'll need to the class. If you haven't picked up your test, then come grab it. I don't want them anymore. Never did. I know. See you guys on Thursday. See ya.